In this lecture, we will investigate the basic principles and various types of electronic visual display. Electronic display devices receive image or video signals and display them on the screen. Then we can see them by our eyes. Let's first see the cathode ray tube, or CRT. Geissler, a German inventor, developed a mercury pump in 1855, which enabled him to construct the first effective vacuum tubes. Crookes later modified these tubes to form the first cathode ray tubes, which led to the discovery of electron. Brown, a German physicist, first demonstrated a cathode ray tube oscillograph in 1897, guiding a narrow stream of electrons to a fluorescent screen. In the 1920s, practical research on a television set using a CRT began. In 1926, a CRT screen was successfully displayed with an electronic signal of a simple figure. Following that, CRT technology advanced quickly, and the CRT became extensively utilized as a display device for TV sets and computer displays. The CRT's best feature as a display device is its low price. That is, compared to other display devices, a CRT display with a good performance and function can be obtained at a relatively low cost. It is also feasible to get a high-definition CRT with a light screen. The matrix address method is used by other electronic display devices to display images on the screen. Other displays have a large number of electrodes and electronic contacts as a result. On the other hand, the electron beam is scanned onto the screen to produce images in the CRT. As a result, the number of electric contacts is extremely low. The CRT's brightness and contrast are also good. The CRT's design can be easily altered to fit its specific application. Since the 1990s, however, many types of flat panel displays with improved functions have been developed. As a result, CRTs are no longer used and have been replaced by other flat panel displays. To achieve a larger screen size on the CRT, the tube length must be increased. That is, as the size of the screen grows larger, the CRT's dimensions and weight increase fast. This was the major drawback of the CRT as a display device, especially for large screen display. A high operational voltage was also required by the CRT, which was a drawback in terms of circuit design. Because the scanning of electron beams is utilized to produce images rather than the matrix address method, image distortion on the screen can occur in the CRT. The CRT is a vacuum tube in which images are formed by narrow electron beams generated by the electron gun hitting a phosphor-coated screen. The CRT is shown schematically in the figure, this figure. The electron gun, anode, diffraction coils, and a phosphor-coated screen are all essential components of the CRT. An electron gun generates electron beam which is subsequently accelerated and focused by an anode. The diffracting coil generates a magnetic field with an extremely low frequency based on the external electrical signal of the images to direct the path of the electron beams to the screen. The horizontal and vertical diffracting coils are two types of diffracting coils. When an electron beam hits the phosphor-coated screen, it generates a bright spot. The screen of black and white television is coated with white phosphor. When the electron beam hits the specific location on the screen, it generates a bright spot. The strength of the electron beam determines the brightness of the spot on the screen. Thus, this figure shows the schematic figure of the CRT. The magnetic field generated by image signal in the CRT tube bans the electrons from the electron guns. The bright spots produce images as electrons strike the phosphor-coated screen. Here. The electron beam is scanned across the entire screen to make an image. Electronic circuits inside the TV move the electron beam in the rest scan pattern across and down the screen to perform the scanning. From left to right, the electron beam paints a single line across the screen. If the electron beam reaches the right end, it swiftly returns to the left, goes down slightly, and paints the new horizontal line. So, new horizontal line. The scanning of the full screen is completed when the electron beam reaches right side of the bottom here. And the electron beam then moves back to the upper left corner of the screen, ready to begin scanning of another image. And ready to move to another image. The figure shows the scanning procedure schematically. The intensity of the beam is controlled by the intensity information signal of the image as it paints each line from left to right, creating different brightness. A basic TV screen normally has 480 lines from top to bottom. Our eyes integrate all of the lines together to recognize them as a single image since the lines are so closely spaced. Normally, the screen is painted 60 times each second. Interlacing and progressive scanning are the two methods for painting the screen. The lines on the screen are produced by raster scanning up and down. Our eyes are unable to pick up individual scan lines across the screen because they are so close together, but they can recognize an image as a whole. The screen of a black and white CRT is coated with a single sheet of phosphor. The screen of a color CRT, on the other hand, is coated with dots or stripes of red, green, and blue phosphors. In the color CRT, there are 3 electron guns. Each electron gun is configured to scan a certain phosphor color. To guide those 3 electron beams, a shadow mask is placed very close to the phosphor coating. So it's a shadow mask. This mask is perforated with very small holes aligned with the phosphor dots or stripes on the screen, On a thin metal plate such as inverter, alloy of iron and nickel, the color CRT is illustrated schematically in the figure. So we have 3 electron guns, red, green, blue electron guns, and we have a shadow mask close to the phosphor screen. This is dots type and this stripe type shadow mask. The 3 information signals are combined and supplied onto the CRT's diffraction plate. Chrominance signal is added for color CRTs. The first signal is intensity information, which generates a different brightness on each location of the screen depending on the image displayed. The horizontal retrace signal, which tells the CRT when to move the beam back to the left end after scanning each line, is the second signal. The vertical retrace signal, which moves the beam from the bottom right to the top left 60 times per second, is the third signal. The electron beams that display images on the screen are controlled by these 3 signals. In addition to the intensity information, the chrominance signal is used to display color on the screen. To make a white dot, for example, red, green, and blue lights of equal intensity at location on the screen at the same time, then we can have the white spot. Red and blue lights of equal strength hit the screen to create a pink spot. The green beam is shut off in this situation. All 3 beams are shut off to generate a dark spot. All of the colors are created by combining red, green, and blue in this fashion. Now let's see the flat panel display. The CRT was primarily utilized as an electronic display for numerous applications until 1980s. However, there has been an increase in demand for a display device with a big screen size and high quality. The tube length on this CRT must be increased in order to achieve a larger screen. On a CRT, however, increasing the screen size indefinitely is difficult. In addition, when the size of the screen grows larger, the size and weight of the CRT grows significantly. As a result, the demand for a display that is thinner, less bulky, and has a higher resolution has driven flat panel display development. Various flat panel displays appeared and were commercialized, including LCD, liquid crystal display, ELD, electroluminescent display, FED, field emitter display, and PDP, plasma display panel. However, only LCD and OLED are widely used, with the others having been driven out of the market. In this table, we can see various flat panel displays. Let's see first LCD. We will explain these displays in detail further below. But in this table, we roughly explain what type display panel displays are. LCD is liquid crystal display, and LCD doesn't emit light. So the other display, there is some process to make light, but in LCD there is no process to make light. So LCD doesn't emit light. Consequently, images on the screen should be produced using the backlight. So backlight is used. The fluorescent bulb was used as a backlight. The backlights, however, are currently made of LED or quantum dot. PDP is the plasma display panel. PDP uses a gas discharge for producing images. Due to its limited lifespan and complex manufacturing process, PDP was taken off the market. Next, field emission display. Field emission generates electrons from sharp tips that strike a phosphor-coated screen to produce image. This FD also off the market because due to the tip's limited life, FPD was no longer on the market. Let's see LED light emitting diode. Both lighting and outdoor billboards use LED technology. Next generation of displays are expected to use micro LEDs. So these LEDs are widely used, especially for lighting, white light lighting. White light can be obtained by this LED, so this LED is used widely used for lighting. Next one is electroluminescence device. Certain elements produce light through electroluminescence. We use electroluminescent organic material in OLEDs. So OLEDs are widely used now for smartphone display. So OLED, organic light emitting diode. The light is produced by electron-hole pairs. Organic material can be used to construct a flexible display. So electroluminescence display is not used now, but if we use the organic, so ELD used the inorganic material, but OLED used the organic material. So this OLED is widely used for TV or smartphone display.